In a home shop, the list of projects is truly never ending. One idea leads to the next, which leads to the next, and so on, in a constantly growing web of dependencies, driven not only by necessity, but also by fleeting whims. In one of my recent projects, one of those fancy universal aluminum fixture plates would have been super handy to have. Making one would require a large uniform flat surface, which can usually be achieved with a fly cutter, but unfortunately all of mine would have been too small to get the job done. I successfully finished that past project without a universal fixture plate, but the appeal of that tool never really left my sights. Of course, before I can make one, I'll have to make something else. I'm going to need a much bigger fly cutter. Okay, before you get too excited, I'm not making a fly cutter this big. That would just be silly. This just happens to be the only stock I have in my shop large enough for the job. I am, however, going to make one about half this diameter, which is still pretty big. Which brings me to the first goal of this build. I'd like to make it exclusively from materials I already have on hand. That includes not only raw stock, but also cutters and other hardware. And to make it even more interesting, I want to design it in a way that it can be adjustable. So this is going to take some planning. To start, I'm going to need a steel arbor to mount this in the mill. My mill has a standard R8 taper, so no creativity is needed here. But one of the biggest factors to a successful fly cutting operation is tooling rigidity. Ideally, the arbor and the wheel would be a single piece, and since that's not really feasible for me, I'll have to make the connection between the two as rigid as possible. To achieve this, I'll include the largest threaded flange I can with the material I have on hand, and to make it even more sturdy, I'll make this end a nice press fit into the wheel. Now for the wheel itself. While I could technically go with a more material conserving rectangular design, I'm sticking with a round design for one main reason: mass. The more mass behind the cutter, the more inertia it will have, and the less deflection there will be as the cutter engages with the material. This will hopefully make for a smoother, flatter finish. The extra mass will also give a sort of flywheel effect, meaning the cutter should be able to really power through deeper passes with ease. A heavier steel would be best for this, but aluminum's all that I have, so that's what it's going to be. For the actual cutting portion of the tool, I want to use indexable carbide inserts, mostly because I like the simplicity of them, but also because the other tooling I inherited from my grandfather used these inserts, so I have a ton of these. To hold the inserts, I'll need, you guessed it, an insert holder. This will be separate from the wheel for a few reasons. Firstly, because it needs to be made of a harder material than the aluminum wheel to take the concentrated loads the insert will see. I happen to have some impact-resistant S7 tool steel that should do the trick. Secondly, because it would be a lot easier to machine the side and back rake angles for the insert on this much smaller part compared to the larger diameter wheel. For this first iteration, I'm choosing a 10-degree positive rake angle and a 0-degree back rake angle. This is close to the arrangement on my current fly cutters, but if for some reason that geometry doesn't work well, I can just make a new insert holder rather than the entire wheel. Lastly, the holder is separate because I want to be able to change its mounting position on the body, making this fly cutter adjustable in diameter. As a rule, fly cutters should be larger than the material being cut, but not too much larger or the angle of attack of the cutter will be too steep and you increase the risk of chipping the tool, especially with brittle carbide. To make the holder adjustable, I'll include a positioning groove and slots in the wheel face. This will give me a continuous range to set the cutter to, while also ensuring the cutter stays on center and maintains the rake angles I define in the holder. To even out the imbalance the tool holder will introduce, I'm including a matching groove on the opposite side of the wheel. This will give me a spot to mount an adjustable counterweight. Of course, I can't forget the little pieces either: an insert clamp for securing the carbide to the holder, and a couple washer plates for mounting the holder and counterweight to the wheel. Then, that's about it. I've been sitting for a while, so I'm really itching to get going on this build. I'll begin with the wheel since most of my machines are already set up for making this part. Before I can really get started though, I do have one small side project I've been waiting to address on the bandsaw. You didn't think I meant all that rust, did you? I'll get to that eventually. For the thicker material cuts I tend to make, the current blade is not the best suited for this. By that I mean the tooth pitch is far too fine. From what I've gathered, I need 3 to 12 teeth engaging in the material during cutting. So I'm switching to a much coarser blade pitch that will hopefully speed up my cuts. The blade is a bit deeper than the one mounted, so adjusting the blade guides is necessary as well. These bearings need to support as much of the blade as possible without interfering with the teeth to ensure that the blade cuts true. For aluminum, I want a cutting speed of about 150 surface meters per minute. So I'll adjust the gearbox settings, then I can cut this sucker out of here. Huh, what do you know? When you properly set up the bandsaw, it cuts way better. Who would have guessed? With the blank cut out, it's over to the lathe. I'm going to have to turn both sides of this plate, so I'll be relying on the chuck jaw faces to keep both sides parallel. For some reason though, my gut is urging me to check that these jaws are actually running true themselves. And it would appear they are not. And by not, I mean there's nearly 10 thou of axial run out. What on earth? I'm going to have to get to the bottom of this. Indicating on the back of the chuck itself, I get the same run out, so the problem must be deeper. This could be really bad. With the chuck removed and indicating on the lathe nose though, I'm getting absolutely no run out here. That would have been the worst case scenario. Big sigh of relief. It must be something in between. Bingo. The chuck backplate isn't running true. I'm not sure the origins of this plate, but I'm surprised my grandfather never caught this. Then again, most forge-all applications are meant to adjust away run out. The solution here is pretty simple, fortunately. I just have to reface this plate. Looking good now. Let's get the chuck back on here and check the jaw faces as well. Problem solved. All four jaws are now within a thou of each other. Alright, let's get back to business. This first side I'll only grab by about 1/4 inch with the jaws. Yes, I just went through a bunch of work to align the jaw faces, but don't worry, that will be relevant in a minute. I'll center the material roughly by aligning my punch mark from before with the tailstock center, and also set up a dial indicator on the face to tap it in within a couple thou of true. Then let the lathe do its magic across the face. This is the largest diameter thing I've turned to date, and I'm surprised how well the finish came out without having to change the feed rates or speeds as I got near the middle. That will do nicely. The rough outside diameter also gets turned down as close as I'm comfortable getting to the chuck jaws. And while I'm here, I'll drop a nice chamfer on the outside before dismounting the stock. To protect the surface I just machined, I'll wrap the jaws in aluminum sheeting, then remount the material fully seated against the jaw faces. Truing up the diameter isn't so simple this time though. I thought I had left myself enough finished diameter to run the indicator along, but that's not the case here. To get around this, I'll have to indicate between the jaws, backing the cross slide out, then back into the same 0 point on the DRO. Sure, this makes an already tedious task even more tedious, but it gets the job done. From here, it's rinse and repeat on this side, facing, turning, and chamfering. One last operation on the lathe is the bore. I'll drill this out with the nearest undersized drill, then bring in the boring bar to finish it out. And of course I have to break these edges as well. Alright, that takes care of the lathe work. I'm not quite finished with the chuck though. If you've been following along with my builds, you might know what's coming next. That's right, the rotary table chuck adapter. What a great tool. Feels like every other project I find myself using this to move work between the lathe and the mill. Definitely time well spent. With everything lined up on the mill, I can work on the insert holder slots. The width of these pockets is somewhat important for positioning the cutting tool, so I'll start with a single milled path down the center of the slot, then cut the perimeter in a climb milling fashion, meaning I'm moving the material in the opposite direction that the cutting edge is rotating. This will prevent the end mill from pulling into the metal and removing more than I want. Climb milling isn't the best practice for a manual machine with lead screws like this, but this is a pretty light cut in aluminum, so I'm not too concerned. To cut the slots for the screws, I'll pilot drill some through holes to start my milling paths. And like before, rather than going right in with the final mill width, I'll use an undersized mill to hog out the material in a stepwise fashion, and then sweep around the perimeter of each slot at full depth. Now it's time for the rotary table to really shine. The arbor mounting holes are oriented 30 degrees from the slots, so I can simply rotate the table that amount and center drill for these. With the table dropped all the way down, I don't have quite enough room for the drill chuck in here, so I'll have to mount the 1/2 inch drill directly in an R8 collet to make these 4 holes. Then switching to an end mill, I can cut the 4 counterbores. By using the quill feed and depth stop, I can ensure that each of the cuts are clean and to a uniform depth. A quick chamfer on these and we can see how a screw fits. Perfect. Other than some light deburring, that's it for this piece. But it's not going to be very useful unless we can mount it in a machine. So, time to start on the arbor. This is going to be mostly lathe work, and a lot of this diameter is going to be turned down. So I'm looking forward to a lot of heavy hogging. But all those heavy cuts are going to put a lot of load on this part. So I'll first face, center drill, and then bring in some tailstock support. Only a short length of this bar needs to be this large of a diameter, but I'm turning as much as I can right now anyway to help with setup later. This first bit of hogging is to form the pin that the wheel will mount to. This will end up being a press fit into the wheel, so the diameter is critical. To make sure the final dimension is exactly to spec, it's important that I let all of the heat from the heavy cuts dissipate before I take the final measurements and cuts. And it basically goes without saying that everything gets chamfered as well. That takes care of the first end, so now it's time for the more intricate stuff. I'll switch to the forejaw this time, and then make adjustments both near the jaws and farther out to bring the material in line. This alignment isn't absolutely critical, but it would be really nice if the fly cutter spun true on the arbor rather than whipping around like an old wagon wheel. Well, maybe that's an exaggeration, but you get the idea. I'll face the end to the final length, then center drill for tailstock support once again. Now this end really gets a lot of material removed, so it was fun to push the lathe and see what kind of beefy cuts it can do. I may have tripped the VFD overload protection a couple times, but hey, you don't know the limits unless you push them. And on this lathe, apparently that limit is a 50 thou depth of cut running 1250 RPM and a chip load of around 20 thou per rev. Not bad. With the major diameter of the R8 taper turned down, I can now reduce the diameter further for the upper part of the arbor, leaving a length to form the taper on, and also turning down the middle relief section. Again, I've left about 20 thou on the end to fine-tune the diameter once the material cools down. And of course I couldn't resist shining this up with some emery cloth. To cut the 16.85 degree taper of the R8 arbor, I'll need to use the compound slide. So to really dial this in, I'll use the dial indicator. Positioning it against the quill of the tailstock, I can adjust the angle until I get the expected amount of change on the dial for a given amount of stroke on the compound. I'll blue and scribe my stopping point for the taper near the mounting flange, then begin taking angled cuts until I reach that mark. I don't usually go by scribe lines when I'm machining, but in this case the tolerance is fairly loose, so this is more than acceptable. I'll sand this as well, and then of course, chamfers all around. The last bit of lathe work will be the threaded hole for the drawbar. This gets a pretty aggressive chamfer that helps the drawbar align inside the mill, and should hopefully prevent everything from cross-threading. Alright, that's it for the lathe. I still need the chuck, so this comes with me over to the mill to mount to the rotary table once again. But now there seems to be an issue. The chuck isn't seating fully against the adapter. It immediately dawned on me what the problem was. So far, I've only ever used the 3-jaw chuck on this adapter, which had the same issue. To correct this, I ended up shortening the cam studs just a bit to make it all work. I filed that away as something I would need to do on the 4-jaw as well, and then promptly forgot where I stored that memory. Until today. But now you're probably wondering, hey, didn't that have an effect on the wheel you machined earlier? Well, yes. But fortunately that only resulted in a 5 thou difference in depth on the 2 slots, which I can live with. Alright, with that issue behind me and the chuck mounted, I can solve the next problem. How to drill the flange holes with this long arbor in the way. There's definitely no room in here for a drill chuck, and I don't have any long center drills on hand. But I do have these. These are tap extenders and have a pretty nice collet mechanism for concentrically locking onto taps. So I'm hopeful they'll keep this center drill running true as well. Nice. The through drill is a similar story with chuck clearance, but fortunately it was just long enough to pass all the way through the flange while still clearing the arbor. The tap extender also let me get the chamfering tool in here, but it's not going to work for the taps themselves. There just isn't enough vertical clearance in here for everything. Instead, I've set up a transfer punch in the spindle to act as a makeshift tap follower so I can get the tap started straight, then bring it out in the open where I can use a proper tap wrench. The last feature on this part is the keyway, which I can't quite achieve from this angle. So I'll stand the rotary table up, and of course tram it back in square with the mill. This leaves the main arbor fairly unsupported though. Good thing I just made a machinist jack that would work perfectly for this. I'll edge find on the arbor to locate the center, and then mill the keyway in a single pass. After a light filing to deburr the edges, this part is complete. But does it fit the spindle? Affirmative. Alright, that takes care of the big pieces. Time to make some headway on the little bits. The insert holder will be made from this piece of S7 tool steel, which should be perfect for this application since it's very impact resistant. I'll cut down enough to form 2 blanks. Well, maybe not. The saw blade doesn't seem to be playing well with this steel. I only got about 1/4 of an inch in before it basically halted cutting altogether. I guess impact resistant also implies cut resistant, and also did a number on that fresh blade I just installed. I've never worked with this material before, so maybe it's just hardened or something. But either way, I don't have all the carbide tooling I would probably need to make all the features on this part. I do have a suitable alternative though. Some good old 4140. Before I can cut this down to size, I do need to swap the blades once again, which of course means readjusting the blade guides again as well. That's more like it. After milling the stock down the width, parting it into 2 separate blocks, squaring up the ends, and tapping 3 mounting holes in each, these blocks are prepped and ready for the more interesting machining, the insert mounting features. These are going to require that the part be set at several different angles. So to make this a bit easier, I'm bringing back the pivot base for the vise. This mounts below the vise and gives an easy way to rotate it to a specific angle. The first angle I need though is 0 degrees, so I'll go ahead and tram this in square and I can get started. The 10-degree side rake angle will be defined by this first cut. So I'll set the block up in the vise with a 10-degree angle block. Then it's just a simple milling operation to form the flat that all the other features will depend on. With that taken care of, I can move on to the 3 holes. One for the insert clamp anti-rotation pin, a threaded hole for the clamp itself, and one for corner clearance of the insert. Now to make use of the pivot plate. I'll loosen the bolts and rotate the vise to the positive 30-degree mark. And to ensure it's really at 30 degrees, I'll mount an angle block against the vise jaw and run an indicator along it to fine-tune the angle. Before I can go cutting the insert pocket though, I first need to locate this part in the mill again. I've defined all the pocket geometry off the center of this hole, so all I have to do is locate it with a drill as a guide and 0 the DRO. Then it's a single pass with an 1/8 inch end mill to form the first side of the pocket. I'll rotate the vise to the negative 30-degree mark, tram and locate the same hole, then cut the second side of the triangular pocket, and also hog out all the middle material. Let's see how an insert fits. Not so good. The corner of the insert hits before the long flat edges, meaning the insert could end up drifting all over the place. That's not going to work. On top of that, I just realized I messed up one of the hole positions as well. I'm batting 1,000 today. I could keep this messed up block as a counterweight for the wheel, but then I would have to look my mistake in the eye every time I use this tool. There's really only one place for this piece now. I'll modify the design slightly and give this another shot. This time around I'm adjusting the hole locations to the correct spots, and when milling the pocket edges I'm offsetting from the center of the corner relief hole by about 10 thou. Alright, that's what I'm talking about. Just enough corner clearance for the insert edges to properly seat. And the holes are no longer dangerously close to one another. That takes care of side 1, but I figured while I'm here I'll mill an insert pocket on the opposite side as well. This will give me the option to mount the inserts at either a 0-degree cutting edge angle or a 30-degree cutting edge angle. The last feature to machine is the cutter clearance behind the inserts. Removing this corner guarantees that the insert is the only thing engaging during the cut. Alright, after some cleanup with emery paper, this is looking great. But it's not ready to see action quite yet. I still have the hardware to make. First up are the insert clamps. Working with small parts in these big machines can be challenging, so sometimes a little creativity is needed. To start, I'll square up the end of another piece of 4140 in the mill, before drilling 2 holes through the full thickness of the stock and also chamfering 2 of the edges. Don't worry, this will all make sense in a second. Moving over to the bandsaw, I'll make a cut down the middle, then separate this from the rest of the bar to leave an odd looking piece like this. Again, stay with me here. Mounting this back in the vise, I can then start taking passes off the top until suddenly this one piece becomes 2 clamps. This just leaves the last face of each that needs to be milled down to thickness, and then a 25 thou step is milled onto each. While that approach wasn't strictly necessary, it allowed me to essentially make 2 pieces with a single setup for each operation, almost like a buy one get one free, or at least 90% off. After a little shining up, these are certainly looking the part. They aren't quite finished yet though. I still have one little lathe job left. I'll chuck up some A2 tool steel rod and start whittling down the diameter until I'm right at an 1/8 inch. I'll part this off, clean up the opposite side, and then these are ready to be driven into place in the clamps. So what does this pin do, you might be wondering? Well, I want to see how well this works, so why don't I just show you. The carbide insert goes like so. Then the insert clamp drops on top and the pin pops into the end hole. This way, when I tighten down the screw, the clamp doesn't try to rotate as well. Nor will it drift around when this tool starts taking cutting loads. The other side is the same deal, though I would only ever be using one side or the other. Seeing this all together, it looks very robust and ready to take the punishment of fly cutting. I could go ahead and bolt this right to the wheel, but then the screw heads would immediately deform the aluminum top. So some simple washer plates are in order. I'll need two, so I'll start by scribing the outlines of each onto a piece of A2 tool steel. Then I can move over to the mill to accurately drill all the holes. And of course drop chamfers on both sides. I'll section these off with the cutoff wheel, then use the belt grinder to bring my edges to my scribe lines. After cleaning up all the edges with some finer grit emery cloth, these plates are ready to go. And that's all the pieces ready for assembly. Now to increase the chances of extending this tool's life, the proper thing to do at this point would be to heat treat the parts. Especially the bits that will see the most force during cutting. But that's a whole rabbit hole I've yet to go down, and honestly I've run out of time on this project. But before I do a final assembly and take this for a test spin, I'm going to give these parts some rust prevention via cold bluing. I've shown this process in a few other videos, but a common question I get is where I get this kit in particular. Mine comes from a company called Caswell Plating out of New York, and they have a couple different versions. I went with the type that includes a sealer that dries to the touch once applied. With the steel parts all blued, I can assemble this. As you might recall, the arbor is a press fit into the wheel. So to ensure that the bolt holes line up, I've inserted some longer studs to keep everything aligned while pressing. The cutting insert gets mounted just like before, and to even out the weight distribution, I'm mounting the counterweight on the opposite side, but just slightly inboard so it doesn't interfere with the cutter path. Alright, let's take this bad boy for a spin.
It's so good. That's so good.
Wow, that looks fantastic. That should work perfectly for my needs on the next project, which was the primary motivation behind this build in the first place. But with the added adjustability and interchangeable insert geometry, I'm optimistic this will serve me on some other projects I have in mind as well. That is, until something else catches my fancy and diverts my attention once again. As always, thanks for watching, and see you next time.